Hi everyone. So in this lecture, we will study refinement of a partition. The concept of partition we have already seen. What is partition of a set? That concept we have seen many questions, a lot of practice we have already done. What is partition of a set? Now we will see what is refinement of a partition. If you have a partition, then how can you refine that partition? Okay, this is the concept for this lecture. This is the topic. So let's start now. So first of all, some recap. Let's see the partition of a set. You already understand what is partition of a set. So what is that? Partition of a set. So if you have a set, let me assume that you have a set S. So you have some set S. Then what is partition of this set S? These are the elements of this set S. Now, partition of this set S means you will, partition of a set means basically a collection of disjoint, non-empty, okay, a collection of disjoint non-empty subsets which cover all the elements of S. That is your partition, right? Yes or no? For example, I can say this is your partition. I can say this is part P1, this is part P2, this is part P3, this is part P4. Okay, this complete is called partition. This is complete is called partition. You can say it is your partition pi1. Okay, this is complete. This complete is partition pi1 of S. So you can see that there are four parts in this. So I can say this is a part. This is a part P2 of partition pi1. Okay, the name of the partition we are saying pi. Okay, this pi we are using for partition. This we are using for partition. Please understand that we are using this for partition, and we are using this P for part. Is this clear? Okay, we are using this pi for partition and we are using this P for part. So this is the concept of partition. You already understand this concept. So we know that what is partition of a set S? Partition means a collection of, so let's see this. What is partition of a set S? That is basically a collection of non-empty disjoint subsets of S, okay, which cover every element of S. This is the definition. Yes or no? Is this clear? What is partition of set S? Very simple. So for example, as you can see, collection of subsets of S which are non-empty, which are disjoint, and they cover every element of S. This is your partition. I hope you understood. Like this is your on your screen. This is the partition. Okay. So in this partition, how many part we have? Can you tell me? In this partition, you can notice this is a part, this is a part, this is part. So there are total 4 parts. Okay, in this partition. And you can also notice that these are disjoint. You can notice this part, this part, this part, and this part. These are disjoint. They are subset of the complete set. This is the complete set. For this complete set, you can notice that these are the subset. These are disjoint subsets, non-empty, and they cover every element of the base set. Is this clear? So very simple. So I hope this point is clear. This is the basically we have already seen this. This is just a recap of partition. So partition of set S means collection of non-empty disjoint subsets of S which cover every element of S. Okay, so if you have any set, you can easily partition it. For example, if you have set of natural number, this is the set of natural number, then you can partition it in many partitions you can create. For example, one partition you can create is like this: odd natural numbers here, even natural numbers here. So you can order this is one partition. Let's call it pi1. Another partition that you can create is like this. For example, I can say that another partition you can create like this. You can say that you can create another partition such that here remainder 1 when you divide by 3. Okay, all those numbers which will give you basically all those numbers x such that x mod 3 is equal to 1. Okay, here all those numbers y such that y mod 3 is equal to 2, and here all those numbers such that z mod 3 is equal to 0. So again, you can note this is also a partition. So partition, the concept of partition is very simple. The partition can be infinite also. So for you can have infinite number of parts also. For example, maybe you have one part in which you have number 1, another part has number 2, another part has number 3. Okay, basically every part has one number only. Every part has only one number. Okay, so like this. So you can notice that, and so on. So here you have, this is another partition pi3. This is your partition pi2. In this partition, there are 3 parts. In this partition, there are 3 parts. In this partition, there are 2 parts. And in this partition, there are infinite number of parts. Okay, so the concept of partition we have already seen. Now, what I can say, like you can see this example, like this is your set 1, 2, 3, and these are the partitions. So, for example, this is a partition. Every part has one element. Okay, there are 3 parts. So you can notice 3 parts we have. Every part has one element. This is another partition. 1, 2. 1, 2 is in one part. Another part has 3. This is another partition. This is another partition, and this is another partition, and so on. So you can easily see these are, and you can see that these are subset. Every part is a subset of the set. This is your set S. So you can easily see, if this is your set S, then you can see this is a collection of subsets of S, such that they will cover all the elements of S, and also they are disjoint and they are non-empty. Okay, so very easily you can see all those concepts. Very easily you can see. Now let's move on. Let's see this. So partition definition, we already know what is a partition of a set. So partition of set means basically you are splitting the set. You are splitting the set into disjoint non-empty subsets, so that every element belongs to exactly one part. Okay, every element of the set, every element will belong to exactly one part, because all the parts are disjoint, all the parts are non-empty. Okay, and all the parts, they will cover every element. So every element will belong to exactly one subset. So very simple. So you are splitting basically. Okay. Now let's move on. So analogy, if you want some analogy, then you can understand the analogy like this. So like, for example, you have apple. Okay, the idea of partition is basically, for example, you have the whole set and you can divide it into parts. So the analogy you can understand, like, for example, your apple, you have an apple and you slice it into pieces. Okay, then that is a partition. Okay, that is called partition of a set. Okay, so very simple. Now let's move on now. So for example, this is a set A, B, C, D, set A. Now what are the partitions? You can see this is a partition in which you have 3 parts. So 3-part partition, this is a 3-part partition. So I can say, for example, I can say that this is, you can call it pi 1. This is a partition. You can call it pi 1. This is another partition. You can call it pi 2. This is another partition. You can call it pi 3. Another partition, you can call it pi 4, and so on. Another partition, you can call it pi 5. Okay, and so on. Okay, so this is another partition, pi 5, and so on. So like this, and so on. So you can notice this is 2-part. For example, this is your another partition. You can call it maybe pi, you can call it maybe pi 10 and something. Okay, very easily. So this is a partition. This is a partition. Okay, this is a partition, and this is a part. So very simple. So very easily you can see. So partition basically means that you are dividing your set, you are splitting your set. You have a set and you are splitting that set. Very simple. You have a set S. You have a set S. Then what is partition? This is your set S. You are splitting this set S into parts. Okay, you are splitting this set S into parts. Okay, into parts, so that they are disjoint from each other. They are disjoint from each other. They are non-empty, and they will cover every element of S. Every element of S will belong to exactly one part. Every element will belong to exactly one part. You can notice every element, it is belonging to exactly one part. Every part is non-empty. Every 2 parts are disjoint. This is the concept of, this is your partition. This is the partition pi of S. Now let's move on. So this concept, now let's see this question from the Kenneth Rosen. This is a question number 41 from the Discrete Mathematics by Kenneth Rosen. So can you tell me the answer? Which of these collections of subsets are partition of 1, 2, 3, 4, 5, 6? Which of these collections of subsets are partition? Which of them is a partition basically? So can you say this is a partition? This is not a partition because these are not disjoint. You can easily see these are not disjoint. So this is not a partition. Okay. Now let's see this one. 1, 2, 3, 4, 5, 6. Yes, this is a partition. You can easily see they are non-empty, disjoint, and they cover all the elements of S. Okay, remember these are non-empty. Look at these. These are non-empty. These are disjoint, and they cover all the elements of your set S. Now let's see this. So 1, 2, 3. Yeah, this is also a partition, and you can see this is not a partition because this does not cover 3. So you can notice 3 does not belong to any part. Does not belong to any part. Okay, so basically B, C, these are the partition. Is this clear to everyone? Let me know. In this, you can notice 3 does not belong to any part. So definitely this is not a partition. And the remaining are the partition. Okay, so this is a partition in which you have 2 parts. 2 parts partition. This is your 2 parts partition. And this is your 4 parts partition. Okay, let's move on now. Let's see this. This is another question from the Kenneth Rosen. Question number 42. Which of these collections of subsets are partitions of -3, -2, -1? So basically from -3 to 3. So which of them is a partition? So you can easily see that this is a partition, right? This is a partition. Very easily you can see this is a partition, even comma odd. Okay, basically odd comma even. So this is a partition because they are disjoint, non-empty, and they cover all the elements of this set S. Let's call it set S. So this is a partition. What about this one? The next, this is not a partition because this 0 is these are not disjoint. They are not disjoint. So this is not a partition. Okay, because these two parts, this part and this part, they are not disjoint. 0 is common. This is not a partition. What about the next one? The next one, -3. So yes, this is a partition, no problem. And what about this one? This is not a partition because 0 does not belong to any part. Okay, does not cover 0. It does not cover 0. Okay, so very simple. I hope all these points are clear. So in this question, A, C, these are the partition. Now let's move on. Now the next concept is refinement of a partition. What is refinement of a partition? This is extremely simple concept, let me tell you. Within one moment, you will understand this concept. Then we will do the complete analysis. Then we will solve all the questions, all the variations, all the results. Okay, we will prove all the results. But this concept is, let me tell you, this is extremely simple. Okay, you will not believe me, but this is extremely simple concept. Let me give you the definition. What is the definition? See, refinement means do more parts. Okay, do more partition, further partition. Refinement means further partition, further fragmentation. Okay, refinement means further fragmentation. What it simply means, refinement is like this. For example, you let me give you one analogy so that you will understand. Can I say this apple is partition of this apple itself? Can I say you have this apple? Let's assume you have this nice apple you have. Okay, how to draw the apple? So I don't like. Okay, let's assume this is a nice apple you have. Then tell me, can I say this is partition of this itself? This apple. Look at this apple. Look at this apple. Okay, let's say this apple A. Can I say this is partition of itself? Like, what are the partitions possible? For example, this is your apple A. Now let's see what are the partitions. What are the partitions of A? Partitions of A. For example, if you want to give this apple to anyone, what you can do? What you can do if you want to give this apple to anyone, what you can do? For example, this is the partition pi 1. This is for yourself. Okay, this is by boys. This is a boys partition. What is the boys partition? What is the boys partition? The boys partition is A itself. Okay, they will eat it completely. Yes or no? This is the boys partition. They will just take it and they will start eating. Okay, so that's it. Now, what is the girls partition? Okay, let's see the pi 2. Okay, so let's see the girls partition. So what they will do? Nice 4 slices will be there. Yes or no? Nice 4 small slices will be there. Okay, small. Okay, so this will be partitioned into, first they will do like this, then they will do like this. So it's like this, something like this. Okay, so you have this. This is your apple maybe. Okay, then what they will do? So they will do this, then they will cut this. Okay, something like this. So you can notice, yes or no? So this is your another partition. Okay, I can say this is your another partition. This apple, you partition into A1, A2, A3, A4. Another, you can have mother partition. Okay, your mother is doing the partition for yours, for you. Okay, so another you can have like, okay, pi 3. It will be like the mother partition. Okay, so it will be very nice. Like, you don't even have to do anything. Basically, just be very lazy. Yes, there will be 8 parts. Okay, so basically it will be here like A1, A2, and so on. There will be total 8 parts. Okay, all you have to do, just eat. You don't have to do anything. Okay, so very simple, that like this, what I'm saying. Now you can easily see these are the partition. This is the concept of partition. But now let's see what is refinement. Can I say this is like refinement? Okay, you are going from here to here. Can I say this is you are refining the partition? Yes or no? Tell me. Can I say this is refinement? Can I call it refinement, that you are refining the partition? Can I call it like refining the partition? This is called basically the refinement. Okay, what you are doing basically, can I say that this pi 2, this is refinement of pi 1. Okay, this is refinement of pi 1. So for this partition, this is the refinement. Refinement means further fragmentation. Please understand. Refinement, you are doing the refinement, means further fragmentation. Further smaller pieces. Further smaller pieces. Further smaller pieces. Pieces means part. Okay, so you can see that. Can I call it that you are basically the refinement? Like this pi 2 is refinement of pi 1, and this pi 3 is refinement of pi 2. Yes or no? So does it make sense? This refinement, is it this word, is it making sense? This word, is it making sense to you that what is refinement? So whenever you think about refinement, just understand this analogy. Just remember this analogy and you will never forget about the refinement. Tell me, now can you ever forget about refinement in your in any question after 2 year, 3 year, 10 year? Okay, if you want to, like, if you are confused what is refinement, then just remember this analogy, that this partition, this partition of the apple is refinement of this partition. This partition is refinement of this partition. Okay, so finally what I can say, that what we can say that basically this is your apple. Okay, this is the apple. This is your apple A. Now for this apple A, you can do some partition. You can do some partition. You can do refinement. See, this itself is a partition, right? Only one part you have. Correct. Can I call it partition P1, pi 1? Yes or no? I can call it partition pi 1 because this basically, no, you are not dividing. Okay, you are not dividing. The complete set is a part. The complete set is one part. So this is your pi 1. Let's refine it. Let's refine it. Okay, let's refine it. So if you refine it, then what can happen? Then you can do like something like this. Now this is a refinement. Now you have A1, A2, A3. Very nice refinement you have. Let's call it pi 2. Let's refine this. Let's refine this. Let's refine this. So if you refine this, then what will happen? For refine this means further partition. Yes or no? Refine this means further partition. So you already have this. Now you already have this. You can do the further partition. For example, you can do this further partition. You can do this further partition. You can do this further partition. Okay, now you have what? Now you have something like this. For example, now you have something like B1, B2, B3, B4, B5, B6. So further partition, yes or no? Is this clear to everyone? So tell me, can I say? So this is the refinement. Refinement means further partition. Is this clear? Further fragmentation. Refinement, you are doing the refinement, further smaller pieces. And if you are confused, who is refinement of whom? Then just remember this analogy. Is this correct? This analogy you remember. This analogy is very important because sometimes you will be confused whether this is the partition of, this is the refinement of this, or this is the refinement of this. See, you will be confused. This is very big confusion whenever you study refinement. Like sometimes you will be confused. Is this refined or is this refined? Are you understanding my point? Okay. Is this refined or is this refined? So you will be confused. So always remember this analogy, that this is a refinement of this partition, and this mother partition is refinement of girls partition, and girls partition is refinement of boys partition, something like that. Okay, so very simple analogy you can understand, that here you can easily see that pi 3 is a refinement of pi 2. Pi 2 is a refinement of pi 1. That's it. So very simple. This analogy you can understand. Now you can easily see that this is your refinement. This is your partition. This partition you can refine. Refine means further fragmentation. So now you can get another. This is refined. I can say this pi 2 is a refined version of pi 1. Yes or no? This pi 2, this is refined version of pi 1. I can say this is refinement of pi 1. Okay, tell me simple question I'm asking, very simple question I'm asking. Can I say this pi 3 is a refinement of pi 1? Can I say this pi 3 is a refinement of pi 1? Can I say? Can I say pi 3 is a refinement of pi 1? Yes, of course it will be. It is transitive. Very simple. It is always transitive because you can see that if you have some partition, let me assume some partition you have. You have some partition. Okay, let me assume you have some partition pi 1. Now what you are doing? You are doing further partition. Okay, you cannot merge them. Are you getting my point? You cannot merge them. You cannot merge it. Further partition. Refine means further partition. Refine means further. Further additional. Further means additional. Are you getting my point? Are you getting my point? Further means additional split. Additional split. You do the additional split. So now what you can do? Now you do the additional split. If you do the additional split, then what will happen? Then this will happen that this you already have. See this part, this you already had. Now you can do further split. Now you can do further split, like you can do something like this. You can do something like this. You can do something like this. So like this. Is this clear? Then you can do further split. Now if I further split it, can I say that is refinement of this? Yes, of course. Okay, this is your pi 2. If I further split, if I further refine it, then I can say that it will be refined version of this also. Let me give you very political analogy. Can you give me political analogy? This further refinement process, can you give me a political analogy? This refinement, can you give me a political analogy? Refinement, political analogy. What is that? Political analogy is like this. There was a time when this was complete India. Now after that, what happened? After that, okay, partition into two parts. So after that, there were two parts. Okay, one is Pakistan, another is India. Okay, then there was refinement. Then there was additional partition. Then there was additional partition, that is Bangladesh. And okay, see, yes or no? So like, okay, something like this. So this additional partition happened. Now there is Bangladesh. And there is India. Okay, so this is the, can I say this? Yes or no? Of course. Okay, this India was there and it got partitioned into three parts. Yes or no? Is this clear to everyone? Please tell me. This is your political analogy. Okay, is this clear? So anyway, I hope you understood the definition of refinement. So let me give you now the definition. This is analogy. The game of analogy is over. Now let me tell you the definition now. Okay, the definition is very simple. So please understand that the refinement, if you have some partition, if I let's assume, so let's assume you have a partition pi 2. Partition pi 2 is a refinement of pi 1. What it means? Is a refinement of pi 1. What it means? Some partition pi 2 is there, and that is refined version of pi 1. What it means? It means like this, that this is a pi 1. This is your pi 1. In this pi 1, you have something. Okay, in this pi 1, you have something, let's assume 3 parts or something. So let's assume you have something like this. Now, okay, in pi 2, what you have? You have basically, like, for example, this got additional partition. Like, for example, let's assume this is Pakistan and this got divided into Pakistan and Bangladesh. Are you getting my point? Are you getting my point? Refinement means additional split. Okay, refinement means additional split. So this is very important, that refinement means additional split. Refinement means additional, more split. Okay, is this clear? Further fragmentation, further smaller pieces, additional split, no merging. Okay, you cannot do any kind of merging or something. No merging or something. Okay, no merging. Basically, additional split you are doing. That is called refinement. So for example, as I told you, this is your pi 1. Now what you do, for example, if you do this, this is your, let's assume this is your some part, and this part you divide into 3 parts. Okay, so now what will happen? Now this will happen. Now this will happen, that this part you already have. This part you already have. Now there are 3 additional parts. Okay, so I can say that So this is your refinement. You are refining. Refining means additional partition, additional fragmentation. So when you refine, then you will get this is pi 1 and this is pi 2 you will get. So I can say that pi 2 is refined version of, I can say pi 2 is finer than pi 1. Yes or no? Yes or no? Like mother partition of apple, okay, that is finer than boy partition of apple. I can say mother partition of apple is finer than girl partition of apple. Are you getting my point? So I can say this is finer than, okay, this word also I can use. I can also use this word. Which word? I can say, what can I say? If I use pi 1 here, what can I say? Pi 1 is what? Pi 1 is coarser than pi 2. Are you getting my point? This pi 1 is coarse because pi 2 is refined version. So it automatically means that pi 1 is, I can say, coarser version. Are you getting my point? You can search for the English meaning on the if you don't know what is the meaning of this in the English word, okay, so you can check on Google what this means. This is basically the opposite of the refinement. Okay, so pi 2 is finer, this is finer, this is refined version of pi 1, then automatically pi 1 is coarser version of pi 2. Tell me, is this clear? Now let's see the definition. So can you tell me, can you okay, simple thing I'm asking, can I say that if pi 2 is refined version, then can I say that every part is a subset of some part here? Like this part is subset of this part. 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 So can I say that every part of pi 2 is a subset of some part of pi 1? This is your definition. So those students who are waiting for the definition, so let me give you the definition, and this definition we will use for analysis. So what is the definition? Pi 2 is refinement of pi 1. It simply means that every part of pi 2 is a subset of some part of pi 1. Please tell me, did you understand it? And also tell me, will you ever forget it? Will you ever forget it? This analogy, if you understand, like two analogy I gave you, Apple analogy and India, Pakistan, Bangladesh analogy. Two analogy you have. So I hope you will never forget. Okay, there are two analogy that you have. Is this clear? Okay, so very simple that this, what is the definition? The definition is like this, that every part of pi 2, because this pi 2 is refined version, so it is more fragmentation. In this pi 2, we have more fragmentation. Yes or no? Every part of pi 2, every part of pi 2 is subset of some part of pi 1. This is the definition. I hope this point is clear. For example, let me take example. Let me take example. Like consider this set of natural number. Consider the set of natural number. Now I am giving, or maybe consider the set of integers. Okay, these are the integers. Now what you do? Now can you give me one partition here? I can give you that some partition. I can give you set of integer itself. Yes or no? I can give you one partition in which only one part is there, set of integer. I can give you another partition. In another partition, let's assume that you have all the negative numbers. Okay. Another partition I'm giving you in which you have all the negative numbers and all the positive numbers union 0. And I'm giving you another partition, that is another partition will be all the negative integers, all the positive integers, and now I separate this 0. Now I separate this 0. Okay. Another partition I'm giving you pi 4, that is odd comma even. That is odd comma even. Okay. Now a simple question I'm asking, can I say pi 3 is partition of, is refinement of pi 1? Simple question I'm asking, can I say pi 3 is finer? Can I say pi 3 is finer than pi 1? Can I say this pi 3 is finer than pi 1? Yes, of course. Okay, it's like the complete apple. This is the complete apple, and this is the, I can say, girls partition of the apple. Yes or no? Something like that. So you can notice this is refinement. This is refinement. So I can say pi 3 is finer than pi 1. True. This is true. What about this pi 4 is finer than pi 1? What about this? Pi 4 is finer than pi 1. What about this? What about this? This statement is true or false? Back to back, I am asking true or false statement. I am asking, can I say this pi 4 is finer than pi 1? Pi 4 is finer than pi 1? The answer is again true. No problem. Again, answer is true. Further split. Now, what can you say about? Can I say pi 4 is finer than pi 4? Can I say pi 4 is finer than pi 4? Pi 4 is finer than pi 4. Yes, true. So this reflexive property, this is called reflexive property, right? Every partition is finer than itself. Okay, it is reflexive. Okay, now the next point, can I say pi 3 is finer than pi 2? Can I say pi 3, this pi 3 on your screen, can I say this is finer than pi 2? Yes, this is finer, right? Okay, this is finer because you are doing the further split. In this, you have two parts. There are two parts here. Now you are doing the further split. You are doing the further split. So something like that. So you can easily see that this is also true. Can I say pi 4? Look at pi 4. Can I say that is finer than pi 2? Can I say pi 4 is finer than pi 2? Pi 4, can I say that is finer than pi 2? Pi 4 is finer than pi 2. Is this further split? Okay, can you further split it and can you create this? From this, can you further split and create this? From this, can you further split and create this? No way. No way. Yes or no? There is no way. So this is a false. Are you getting my point? Array, see what I am saying. Let me take simpler example. Okay, if anyone has confusion, let me take simpler example. Let me take a simpler example. Consider this example. Consider this set A. Okay, in this set A, you have 1, 2, 3, 4. A simple example I am taking. Now I am giving you a partition in which you have, for example, 1, 2 is together. Okay, a partition I am giving you in which 1, 2 is together, and here 3, 4 is together. I am giving you pi 2. I am giving you pi 2 in which 1, 3 is together, 2 is separate, 4 is separate. Can I say this pi 2 is, tell me, can I say pi 2 is finer than pi 1? Can I say? Can I say pi 2 is finer than pi 1? Can I say this is refinement? Can I call it refinement? Tell me, a simple question I am asking. Can I call it refinement? This, can I call it refinement? This is not refinement, right? Yes or no? Can I call it refinement? Can I call this refinement? The answer is no. This is not refinement. This is not refinement. Like, refinement means further split. Are you getting my point? Refinement means further split. You can easily say, okay, apply the definition. Okay, forget about everything else. Apply the definition. See, refinement means further split. Further split means, for example, 1, 2 you split into 1, 2. Okay, further split. This is not further split. Like, how can you do this? Yes or no? Are you getting my point? How can you do this? How can you do this? Okay, just apply the definition. What the definition is saying, Mavit? Mavit, what the definition is saying? Pi 2 is refinement of pi 1. What the definition is saying? The definition is saying that every part of pi 2 is a subset of some part of pi 1, right? Yes or no? Pi 2 is finer than pi 1. What it means? If and only if every part is subset of some part. Is this correct? Is this correct that every part of pi 2 is a subset of some part of pi 1? This is false, right? This is not a subset of any of them. Yes or no? This 3, 4 is not a subset of any part. There are two parts. This is a part. This is a part. Please understand, there are two parts in the pi 1. In the pi 1, there are two parts. In the pi 1, there are two parts. In one, you have 1, 2. In another, you have 3, 4. There are two parts. Can I say this is a subset of any part? Is this subset of this part? No. Is this subset of this part? No. Okay. So that is false, right? Yes or no? Can I say that every part of pi 2 is subset of some part of pi 1? This is false. So this is not a refinement. Is this clear now? Is this clear now? Please tell me. Let me know. So this is very important definition. This is extremely important definition that, okay, again, I'm telling you this definition. You have some set you have. Let's assume you have some set A. Okay. And for this set, you have two partition. You have two partition pi 1 and pi 2. There are two partition. One is pi 1, another is pi 2. Now, when can I say that pi 1 is a refinement, or I can say pi 2 is refinement of pi 1. When can I say? Is a refinement of pi 2. So when can I say? Remember this pi 2, okay, this is refinement of pi 1 if and only if, this is very important that every part, okay, I am saying every part of pi 2, every part. So let me write it in capitals. Every part of pi 2 is a subset of some part of pi 1 is subset of some part of pi 1. Okay, is this clear? Is this clear now? The definition, analogy I have given to you, definition I have given to you, is this understood? Okay, let's come back to this question. Let's see here. So can I say pi 4 is finer than pi 2? Can I say? Can I say this pi 4? Can I say this is refinement? Mavit, can I call it refinement? Can I call it refinement? This is not refinement, right? Yes or no? Refinement means, can you further split it and can you get it? By further splitting it, can you get it? Can you get it? You cannot get it, right? Yes or no? Or you can say like this. See, this is not a subset of this. This is not a subset of this. Yes or no? Can you notice this is not a subset of this one? Odd, array, this is also odd number. Mavit, this is also odd number. -3 is also odd number. -5 is also odd number. -3, -5, -11, -9, these are also odd number. Is this clear? Okay, so remember this, like -3, this is also odd. This 0 is even. This 0 is even. This -10 is even. -11 is odd. Okay, anyway, so is this clear that this is false? Pi 4 is finer than pi 2. This is false. What about pi 2 is finer than pi 1? What about this? Can I say pi 2 is finer than pi 4? Can I say pi 2, this pi 2, can I say this is refinement? Can I call this refinement? Can I call this refinement? Can I call this one refinement? Again, this is not a refinement because you can see this is not a subset of any of them. This is not a subset of any of them. So this is also not a refinement. Just use the definition. So this is also false. I hope all these points are clear. So remember, refinement basically means that just use the definition. From now onwards, we will use only the definition. The intuition, the analogy is fine. See, analogy will help you remember this concept for a long time. You will never forget it. If you remember the analogy of political analogy, India, Pakistan, Bangladesh, that analogy, or you can remember the analogy of Apple analogy. Okay, so this analogy will help you basically remember this concept, remember this definition for all the time. But remember, the definition is very important for the complete analysis. For the further analysis, the definition is very important. And what the definition is saying, that, okay, you have P comma Q, these are the partition of S. P comma Q, these are the partition of S. Then P is refinement of Q if every P is refinement. P is refinement means basically P is finer than Q. Okay, it means that P is a further fragmentation of Q. P is further fragmentation of Q. Yes or no? Is this clear? P is a further fragmentation of Q. From P, you are doing the further fragmentation. You are doing the further fragmentation. So you can see that this P is a further fragmentation of Q if every part of P is a subset of some part of Q. Like for example, let me assume that this is a let me assume this is your q. Let's assume this is your q. Then how can I do the refinement? How can I do the refinement? I can do the refinement like this. Yes or no? I can do the refinement like this. Do you agree or not? Is this clear to everyone? So remember, this is your q. Then how can I do the refinement? This is the p. This is the p. So like this, you can do the refinement. So you can do the refinement like this. You can do the refinement like this. This is also refinement. So now I can say this is refinement of q. Okay, I can also call it this is refinement of q. I hope all these points are clear. Now let's move on. Now let's see this question. So for example, you can see this is your set A 1 to 15. Consider the following set whose elements are themselves. Okay, so you can see this is partition, right? This alpha is a partition, correct? Look at this on your screen. You can see that this is your set A. The set A is given to you. Okay, this set A, that is this. Now the question, we have a partition. So this alpha is a partition. You can clearly see this alpha is partition of A. Okay, now you consider another partition. Sorry. Yeah. Okay, let's consider another partition. So this alpha, let's call it pi 1, and this is your pi 2. Can I say pi 2 is refinement of alpha? Can I say this pi 2 is refinement of alpha? You can easily see that. See, very simple. Basically, further fragmentation. Yes, this is further fragmentation. You are doing further split. You can see that you are further splitting it. Okay, further splitting it. You are further splitting it. Now is the definition clear? You are further splitting it. So I can say pi 2 is refinement of pi 1. This pi 2 is refinement of alpha. Okay, clear? So I can say this pi 2 is finer than alpha. I can say this pi 2 is a refinement of alpha. I can say this alpha is coarser than this is a coarser than pi 2. So very simple. So these are the simple words. Or I can say this pi 2 is a further split. It's a further fragmentation of alpha. Okay, clear? Okay, now let's see this. So look at this this question. How many refinements of this partition are there? So before we see this, this may be a complicated question. Before we see this question, let me ask you a simpler question. Consider this question. Let me ask you this is the question that I'm asking. So tell me, how many refinements are there? How many refinements of this partition? This partition is given to you. Okay, this partition, let's call it pi 1. This partition is given to you. How many refinements you can create? See, whatever refinement you do, this will come as it is. Do you agree? This will come as it is. Whatever refinement you do, this will come as it is. Do you agree or not? Yes or no? That this will come as it is. Whatever refinement you do from this phi 1, whatever refinement you will do, what will happen? Whatever refinement you do, what will happen? This in the refinement, this G will come as it is, because you cannot do further fragmentation of this. This is only one element. So further fragmentation not possible. Further fragmentation not possible for this also. But here you can do further fragmentation. So here, how many further fragmentations you can do? How many choices for this one? Either you keep it as it is, or you keep them separate. Only two ways, yes or no. Do you agree? Only two choices. Either you keep them as it is, or you keep them separate. Only two choices for this. So we have two choices for this. And similarly, we have two choices for this. So finally, answer will be what? What are the two choices? The two choices are either you keep this as it is, or you keep it separate, or you keep it separate. So two choices, two choices. So finally, how many refinements are there? The answer will be 2 into 2 into 1 into 1. The answer will be 4 refinements are there. Please tell me, did you get it? See, there are 4 refinements. And what are those 4 refinements? Also, let me tell you. Let me also tell you what are those 4 refinements. So the 4 refinements that we have, the 4 refinements, let me give you. All the 4 refinements I can give you. So the 4 refinements are like this. What you have? For example, AB you keep, so this as it is. Okay, F comma G. So this partition is itself a refinement of itself. Okay, similarly, what you can do? You can split A comma B. You can split this A comma B. You can keep this CD as it is. What you can do? You can split this AB, you can keep as it is. This AB you can keep as it is. C comma D you can split. Or what you can do? You can split A comma B also, C comma D also. Is this understood? Is this question clear to everyone? Is this crystal clear to everyone? Let me know. So can I ask you this question now? Now can I ask you this question? How many refinements can you create from this partition? A partition is given to you, this partition pi 1. How many refinements can you create? Refinement means further split. Okay, refinement automatically means further split. So how many can you create? This pi 1 is given to you. This pi 1 is given to you. This pi 1 is something like this. In the pi 1, what you have? In the pi 1, A, B are together. C, D, E are together. F is separate. G is separate. So whatever split you will do, what will happen? What will happen? So whatever refinement you do, what will happen? Whatever refinement you do, what is going to happen? Tell me. In any refinement, there is no further split of F. Yes or no? F will have its own room. G will have its own room. Do you agree? They will have its own room. Some split you can do here, some split you can do here. Yes or no? So for A comma B, how many choices are there? Can you tell me? For A comma B, how many choices? There are 2 choices. Either you keep them together or you keep them separate. For CDE, how many choices? For CDE, for this CDE, how many choices? For the CDE, either you keep them separate, either you keep them together, CDE, or what you do, you make 2 parts. See, either you make 1 part, either you keep them in 1 part, either you keep them together, or you create 2 parts. When you are creating 2 parts, how many choices? Tell me. When you create 2 parts, how many choices? 3 choices. Yes or no? 3 choices if you create 2 parts like CDE or CED or CD or DEC. So there are 3. And how many 3 parts you can create? Only 1 3 part you can create, CDE. So 4 choices, yes or no? So total, sorry, 5 choices. So total 5 choices for CDE. So answer will be what? Answer will be 2 into 5 into 1 into 1. That will be 10. Please tell me, did you get it now? Did you understand now? Please tell me. Let me know. Let me know, did you understand now? Is this clear to everyone? Is anyone has any doubt? Okay, so very simple. See, now let me tell you actually what is happening. See, very simple things are happening. See, initially, let me give you a set. We already know, for example, if I give you a set and which has 3 elements, A, B, C, and if I ask you number of partitions, then what that will be? Number of partitions, forget about refinement. If I ask you number of partitions, what that will be? That will be 5. Yes or no? That we have already seen, number of partitions will be 5. How that number of partitions will be 5? Because you can create 1 part. 1 part partition, there will be only 1. Okay, so number of ways will be 1. You can create 2 part. You can create 2 part, 2 part, 2 part. So in the 2 part, there are 3 ways. One person will be separated. Yes or no? One person will be separated. One person will be separated. Correct or not? Are you getting my point? Okay, so 2 parts. You can also create 3 parts. Only one way to create 3 parts. All will be separated. All will be separated. There are 3 parts. So total, okay, how many? Number of partitions will be 5. So for example, let me give you a partition. Consider the partition. I am giving you a partition pi. And in this partition, let me assume that you have 1, 2. You have 3, 4, 5. You have 6, 7, 8, 9. And then you have 10. Now tell me the answer. How many refinements? How many refinements of pi? How many refinements of pi? Tell me. So the answer will be very simple. Because of this, you will get 2 choices. Because of this, you will get 5 choices. Because of this, you will get 15 choices. And because of this, you will get 1 choice. And the answer that you will get, will be this. Okay. So that will be 150. Very simple. Let me ask you another question. Let me ask you this question. Consider this partition. Consider this partition in which you have 1, 2, 3, 4. Only basically the entire set is one part. Okay. Are you getting my point? So your set itself is 1, 2, 3, 4. And this is your partition. Now, how many refinement of pi? How many refinement of pi? How many refinements of pi? So this is your set. For this set, this is the partition that is given to you. This partition is given to you. Basically, the entire set is the partition. Okay. The set itself is the partition, basically. Only one part you have. How many refinements are there? Can you tell me? Now. So very simple. The answer will be 15. So can you notice that for the set, every partition will be a refinement. Yes or no? Are you getting my point? For this set, every partition is a refinement. Are yes or no? For this set, every partition is refinement. Every partition of this set is refinement. Every partition is a refinement of it. Is a refinement of S. Is this clear? Every partition is refinement. So the answer will be 15. So how many refinements you can create from this? So the number of refinements, what that will be? Number of refinements will be 15. Because for this set, every partition will be a refinement. Yes or no? Every partition will work as a refinement of this set S. For this set S, every partition is going to work as a refinement. So you can notice that the answer will be 15. Mavit, is this clear? Tell me. Mavit, please tell me. Is this clear? Let me know. If anyone has any doubt, you can ask. So simple topic. This is not a complicated topic. Okay. Mavit is saying that, but every part has 2 choices. Array, there is only one part. Look at the partition. In this partition, only one part is there. Only one part is there. You don't have, see, only one part is there. Okay. And how many? So it is, remember, there is only one part. In this pi, there is only one part. See, this is the partition and this is a part. See, look at this. This is your part. Only one part is there. This is part 1. That's it. So how many partitions how many splits you can create? For this, how many split you can create? 15. Is this clear now? Okay, let's move on now. So let's see this. So assume you have a base set S. If your base set is S, then P, QR, then all these things are same. Yes or no? P is refinement of Q, is same as P is finer than Q, is same as Q is coarser than P, and is same as P is further fragmentation of Q. So all these things are same. All these statements are same. Yes or no? Now let's move on. So you can see that when can I say P is refinement of Q? P is refinement of Q if and only if P is refinement of Q. Remember, P is a refinement of Q, means further fragmentation of Q is P. It means that every part of P is a subset of some part of Q. Okay. So this is the definition. Always apply the definition, nothing else. Now let's see this question. Can you see that? This is your set S. This is your partition in which you only have one part. See, in this, you can notice only one part you have. In this, there is only one part. There are 2 part, 3 part, 4, and so on. Now you can easily see that Can I say this is, can I say P2 is finer, P2 is finer than P1? This is refinement, yes or no? Yes or no? This is refinement. You can basically, you are doing the further split. Again, you are doing the further split. You are doing the further split. See, you are doing the further split, right? Like this, you are splitting into this. So this is also further split. This is also further split. So I can say that in this example, you can easily see that every pi is a refinement of previous. Okay, every pi that is refinement of the previous one. So very easily you can see. Now let's see this question. So tell me a simple question I'm asking. If you have two relations, like this is my question. Let's assume you have set of integers. Okay, your set is set of integers. This is your base set. Your base set is set of integers. Now let me define two equivalence relations. I am defining equivalence relations. One is I am defining R1, another I am defining R2. R1 is basically congruent to modulo 3 and R2 is congruent to modulo 6. Now you tell me what will happen. See, now you can easily see that what this will create. This will create three equivalence classes, right? Yes or no? Look at this. This will create how many equivalence classes? This will create three equivalence classes. So can I say that this will partition our base set into, yes or no? Because of this R1, our base set will partition into three categories. Our base set that is going to divide into three categories. And because of this R2, our base set integers is going to divide into 6 categories. So there will be 6 categories. Okay, now you tell me a simple question I'm asking. Can I say that every part here is subset of some part here? Can I say every part here is a subset of some part here? For example, you can notice that here you will have all those numbers like 1, 4, 7, this type of numbers you will have. Okay, which will give you remainder 1. Okay, here you will have all those numbers which will give you remainder 2. And here all those numbers which will give you remainder 3. Similarly, here all those numbers which will give you remainder 1 when you divide by 6. So when you divide by 6, they will give you remainder this. Okay, and so on. Next, they will give you remainder 2. Like for example, 2, 8, and 14, and so on. Next, you can notice they will give you remainder 3. They will give you remainder 3. For example, this 3, 9, and 15, and so on. They will give you remainder 4. For example, 4, 10, 16, and so on. They will give you remainder 5, like 5, 11, and so on. They will give you remainder 6, 12, 18. Now you tell me, can I say here you will have 6 equivalence classes? So tell me now, can I say this R2, can I say this is finer than R1? Can I say that everything is subset of this? For example, you can notice this equivalence class, this part is subset of this part. Okay, you can also see that this part is subset of this part. 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 And this part is subset of this part. So can I say this R2 is finer than R1? Yes or no? Can you notice that I can say R2, okay, I can say this equivalence relation is finer than R1. Yes or no? This R2 is finer than R1. Is this clear? Tell me. So this modulo 6, this is finer than modulo 3, isn't it? I can say this modulo 6, okay, is finer than modulo 3, then congruent to modulo 3. Yes or no? Isn't it? Please tell me, is this clear? Very simple. What about this? Can I say this is finer than, can I say this is finer than modulo 2? Can I say this is finer than modulo 2? Tell me. This is true. Can I say this modulo 3 is finer than modulo 2? Tell me. Congruent to modulo 3, can I say this is finer than modulo 2? The answer is no. The answer is no. You can clearly see that here you will get two parts which will be odd, even. And here you will get three parts which will be like this. As I told you, 1, 4, 7, and so on. 2, 5, 8, and so on. And 3, 9, 6, 3, 6, 9, and so on. You can notice they are never this. You can notice this is not subset of any of them. Correct? This is not subset of any of them. Similarly, this is not subset of any of them. So you can notice they are not finer than each other. Okay, very simple. So I hope all these points are clear. Is either a refinement of the other? Can I say any of them is refinement of another? The answer is no. They are not refinement of each other. Okay. Now, I hope all of you understood the refinement. So anyone has any doubt at this point of time? At this point of time, do you have any doubt? Let me know. Okay. So now let's see the properties. The properties of refinement. So again, I am telling you that this is just to tell you this definition we will use. Okay. Which definition? Refinement of partition definition we will use now. The definition is very important. Refinement of a partition. If you have a partition, then refinement means you do the further fragmentation. Okay. So you have a partition pi. This is your partition pi. And in this partition pi, let's assume these are the parts. Then refine. If you do the refinement, then what it means? It simply means that you will get another, and such that you are basically further partitioning. You are further partitioning. So something like that. So this is called refinement. Okay, this pi2 is refined version of pi. So this definition is extremely important, that every okay, this pi2 is refined, or I can say refinement of pi1. What it means? Refinement of pi1. If and only if, okay, this pi2 is refined. This pi2 is refinement of pi1 if and only if, because this pi2 is refinement, it means this is further partition. Okay, from this pi1 you are further partitioning, so you are getting pi2. So this pi2 is refinement of pi1 if and only if every part of pi2 is a subset of some part of pi1. Okay, every part of pi2 is subset of some part of pi1. This definition we will apply now. Now let's see the properties of refinement. So first is this. So let the base set, this is your base set A, B, C, D, E. This is the base set. Now the partition, can I say this partition? Can I say this is refinement of every partition? Tell me, simple thing. It's like mother partition. Remember mother partition. If you put every element in a different part, every element you put in a different part, basically every element itself is a part. One part has one element. Can I say that is the most you can do? That is the most refinement you can do. Yes or no? If anyone asks you, what are the most refinement you can do? What are the maximum refinement you can do? Maximum refinement, maximum fragmentation. What are the maximum fragmentation you can do? That is, every part has only one element. One element is one part. Okay. So can I say that this is singleton? Yes, very good. So you can see that this partition, okay, this partition, you can note this partition is a refinement of every partition of S. Yes or no? This partition is refinement of every partition of S. So, okay. So very simple. I hope this point is clear. So here, one thing I just want to tell you, for example, let's assume you have a base set. You have a base set A, which is 1, 2, 3. Then you can easily see that this part, look at this refinement. Which refinement? Look at this refinement. Sorry, this partition. Look at this partition. This partition is refinement of every partition. Yes or no? This is refinement of every partition. Basically, okay, if you refine anything, you can get it. Okay, if you refine anything, like for example, basically I'm saying that this one, this partition, this 2, this 3. Look at this partition. Okay, look at this partition. Let me call it pi. Now you can see that whatever partition you take, if you refine it, you can get it. Yes or no? Whatever partition you take, you can refine it. For example, you can take the entire partition. Okay, you can take this partition, or you can take, for example, this partition, like where you have 1, 2 together and 3 together. And similarly, you can, for example, you can have this partition where you have 2 comma 3 together and 1 separate. So basically, whatever partition you take, if you refine it, you can get it. This is the most refinement you can do. Can I say? So this is also called the finest partition. Is this clear? So remember, this is the point. This is also called finest partition. Is this clear to everyone? So if you have a set A, in this set A, let's assume you have A1, A2, and so on, AN. This is your set A. Then look at this partition. Look at this partition pi. Okay, what is this partition? Where A1 is separate, A2 is separate, A3 is separate, and so on, AN is separate. So this partition is called finest partition. Is this clear to everyone? Please tell me. This is called finest partition. This is the maximum refinement you can do. This is the finest partition of A. Is this clear? Is this word clear? Finest partition. So this is the finest partition. This is the maximum partition you can do. This is the maximum refinement you can do. Sorry. Maximum refinement you can do. So this is the finest partition. Now the next. Can I say every partition is refinement of this partition? Can I say every partition of S is a refinement of this partition? Like every partition, whatever partition you do, that is a refinement of the entire set. Yes or no? Is this clear? So every partition of S is a refinement of this partition. One part partition. Yes or no? I can also say that every partition of S is a refinement of one part partition of S. Correct? So one part partition of S. So I can easily say that every partition will be refinement of one part partition of S. So very simple. So can I say this is the coercer? This is the most coerced set. Can I say? If you have a set S, then can I say this? Look at this partition. Look at this partition where only one part you have. So can I say this is the coerced? Can I say this is the coerced partition of S? Can I say? Yes or no? This basically least refined. This partition is the least refined partition. I can say this is the least fine partition, least refined partition. Okay, is this clear? Let me know. Now the next, reflexive property. Now please understand, now the base set is this. The base set is set of all partition of set S. This is the base set. So now the base set is this. What is the base set? Set of all partition of S. This is the base set. Okay, this is your base set in which you have all the partitions. Now you tell me, if you have all the partitions, then can I say every partition is refinement of itself? Yes or no? Every partition is refinement of itself. So refinement relation is basically reflexive. Yes or no? Because every partition will be refinement of itself. Very simple. Now the next point you can see that, can I say if this is your base set is set of all partitions. Set of all partition is the base set. Can I say refinement relation is symmetric? Sorry, antisymmetric. Refinement relation is antisymmetric, right? Yes or no? That is antisymmetric. Why that is antisymmetric? Can you prove it? Can you prove it that a refinement relation is antisymmetric? Tell me. Can you prove this? What is the antisymmetric definition? Can you tell me? What is the antisymmetric definition? What is the definition? Antisymmetric says that, okay, antisymmetric says that if something related to B and B related to A, then they must be same. This is the definition, right? Yes or no? This is the definition of antisymmetric. If A related to B and B related to A, then they must be same. Now you apply this concept in the refinement. Now consider a set. Let's assume you have a set, base set A, or maybe a base set, you can take base set S. Now let me assume there are two partitions. You have a partition pi 1 and there is a partition pi 2. Okay, there are two partitions. Assume pi 1 is refinement of pi 2 and pi 2 is refinement of pi 1. Then what will happen? So these are the partition. So this is a partition and this is also a partition. Now assume that Assume that pi1 is refinement of pi2, and pi2 is refinement of pi1. Then what will happen? Tell me. If this happens, that pi1 is refinement of pi2, pi2 is refinement of pi1, then what will happen? Tell me. Tell me then what will happen? Array, very simple, right? See, look at this pi1. In this pi1, this pi1 is refinement of pi2. What it means? Whatever part you take, that part will be subset of some part here. Agree or not? Yes or no? So whatever part you take here, in this what you do, you take any part. So consider this part P1. This is a subset of some part here. This is subset of some part here. So for example, let's assume here you have some part, let's assume B1. Okay. So B1 of pi2. So this part P1 is subset of part B1 of pi2. Part B1 of pi2. Now tell me, if this pi2 is refinement of pi1, then what will happen? Then this B1 is also subset of someone, yes or no? Then this part B1 is also subset of someone, yes or no? Is subset of some part of pi1. Is this clear? See, take your copy pen. If you are not understanding, take your copy pen. I am saying that this pi1 is refinement of pi2. It means take some part P1 in this pi1. So this part P1 is subset of part B1 of pi2. Now I am saying that if pi2 is refinement of pi1, then part B1 is subset of some part of pi1. Now you tell me a simple thing. You tell me this part B2, there is some element, right? There is some element in P1, correct? Like for example, this assume there is some element. For example, assume some element A belongs to P1. Then tell me where this A belongs. Simple question I am asking. Then where this A belongs? This P1 is subset of B1. So automatically this A will also belong to B1, right? Yes or no? This A will belong to B1. Now this B1 is subset of some part. Is it possible that B1 is subset of some part other than P1? Is it possible that B1 is a subset of some part other than P1? It is not possible, right? Because all the parts are disjoint. Okay, are you getting my point? See, B1 contains A1. B1 contains A. If this is subset, if this B1 is subset of some part of pi1, then that part must be P1, yes or no? Then it automatically means that this should belong to P1. And it simply means that B1 and P1 are same. It simply means that B1 and P1 are basically same. B1 is equal to P1. If you understood this proof, if you understood, very good. If you did not understand, then just there is no problem. You can just remember this. See what I'm saying. If this happens, then this will happen. So this is what I want to prove. I want to prove that this is what I want to prove, that if pi1 is refinement of pi2 and pi2 is refinement of pi1, okay, then what I want to prove? I want to prove that they will be same. Okay, so from this I am proving, from this you can prove that they will be same. You can say that pi1 and pi2 will be same. Okay, this is what I want to prove. Antisymmetric property I want to prove. This is the antisymmetric property. If you understood the proof, very good. If you did not understand, let me try once more. Okay, one more time I am trying. So, okay, let me try one more time. Let me try. If you don't understand, do not worry about it. Okay, but let me try one more time. Maybe you can take your copy pen. If you do not take your copy pen, anyway, you will not understand. Okay, so please don't watch it like a movie. You can do it yourself. All the topper students, all the intelligent, or I can say all the students who will top the GATE exam, they work it out themselves. Okay, whatever they study, they do it. So remember, this pi1 is refinement of pi2. This is refinement of pi2. Now assume there is some element A. Okay, some element you assume some element A, and that belongs to P1. Okay, that belongs to part P1 of pi1. Okay, is this clear? So just assume some element, there is some element A that belongs to part P1 of pi 1. Okay. Now, by the definition of refinement, by the definition, what will happen? By the definition, what will happen? This P1 will be subset of B1, correct? This P1 will be subset of part B1 of pi 2. Okay, very simple. By the definition, this will happen that this P1, this part will be subset of B1 of pi 2. It automatically means that A belongs to B1 now. Now you tell me, can this A belong to some other part of pi 1? Can this A belong to some other part of pi 1? This A belongs to part P1 of pi 1. Can this A belong to some other part of pi 1? It cannot happen, because every element will belong to exactly one part of the partition. Okay, in any partition, whatever partition you take, every element will belong to exactly one part of that partition. They are disjoint, non-empty, and they cover all the elements. Okay, this is the definition of partition. In any partition, every element will belong to exactly one part. Okay, now you can easily see that A belongs to B1. Now look at this. Pi 2 is refinement. This pi 2 is refinement of pi 1. In this pi 2, there is a part B1. In this part, so that will be subset of what? That will be subset of some part of pi 1. Which part? Tell me. Is it possible that this B1 can be subset of some other part of pi 1? That is not possible, because A belongs to B1. A belongs to B1. So if B1 is a subset of some part, then that part has to be P1. Okay, it should be P1. It must be P1. Now you can see that. Now you can see what is happening. Now you can see B1 is a subset of P1. B1 is subset of P1, and P1 is subset of B1. So from here, what I can say? I can say P1 is equal to B1. They are basically same. So that's it. This is the proof. So remember, so this refinement is anti, this refinement relation that we have, this refinement relation on set of all partitions, is anti-symmetric. It is anti-symmetric. It is anti-symmetric. Okay, let me know. Mavit is saying that, sir, is this relation finally going to become a Boolean lattice? No, it will not become a Boolean lattice, but it will become a lattice. Mavit, you are going in the right direction. It will become a lattice. Ultimately, it is going to become a lattice. Okay, I will tell you, don't worry. So anti-symmetric. So now the next is, this is your base set of all partitions, set of all partitions of set S. Then there is transitive also. Refinement relation is transitive also. Very simple. Because if you have pi 1, you refine it, then you are doing the further partition, and you again refine it. That is further partition. Yes or no? You can easily see that. From here you are doing some further partition and you are getting this, further partition and you are getting this. So definitely you can easily see this is a refinement. Yes or no? Is this clear? Let me know. Is this clear to everyone? So because from pi 1, you are doing further partition, some further partition you are doing, you are getting pi 2. From pi 2, you are doing some further fragmentation, you are getting pi 3. So definitely I can say that this pi 3 is further fragmentation of pi 1. So this is a transitive also. Now you can finally see that refinement relation on set of all partitions. This is reflexive, anti-symmetric, transitive. What this is called? This is called partial order. This is the final thing, that refinement relation is a partial order on set of all partitions of a set S. It is a partial order. Is this clear? So if you have, let's assume you have any set S, then you can see that this set of all partitions, okay, this pi, which is set of all partitions, and this refinement, here this pi, I am assuming this pi is, it's like subset, it's like pi 1, pi 2, and so on. Okay, so this pi is basically, what is this pi? This is set of all partitions of S. all partitions of S. This entire thing is a poset. This entire thing, this is a poset. I hope this point is clear. Let me know. See, everything I have told you step by step. Did you understand? If you did not understand some proof, the anti-symmetric proof, if you did not understand, forget about it. Okay, this anti-symmetric, this proof, if you did not understand, if you have any doubt, if you have any confusion, forget about it. Okay, so don't worry about it. Now, Mavit is asking, sir, what is the set cardinality? See, how many partitions are there? That is complicated to count. Okay, Mavit, that is complicated to count. They will not ask you. So, for example, if I ask you how many partitions are there, that itself is complicated to count. Yes or no? If I ask you, if I give you n equal to 10, then you cannot do that. In the gate exam also, they will not do that. Okay. Are you getting my point? Number of equivalence relation, that is very complicated to count. There is no, I can say, easy formula. There is no straightforward formula. There is Bell number. There is a very, I can say, there is a Bell number formula is there, but that formula is very complicated. Never, never, never apply that formula. Whenever someone is applying that formula, it simply means that they don't know they cannot handle the variations. If one student is applying the Bell number, let them apply. Okay, let them apply. They don't understand the concept. They don't understand the intuition. Okay, they cannot handle the variation. Some variation they will not be able to handle. Okay, anyway, so these things are not easy. How many partitions are there? How many refinements are there? These things are not easy to calculate. So don't worry. Just the whatever we have seen, that is enough. Is this clear? Now let's see this question. Now we will see some question. But before that, let me ask you one question from my side. Let me ask you one question from my side. So consider this set. In this set you have, let's consider this set A, B. How many partitions are there? Tell me, what is the set of partitions? Okay, this is the set of all partitions. How many partitions are there? Set of all partitions. So there is partition pi 1, that is this S itself, right? Okay, this S itself, basically together. Okay, you can also write it like this. You can also write it that they are together, this AB together. There is another partition. What is that? The another partition is they are separate. The another partition is they are separate. Okay, so there are only two partitions. Yes or no? Now you tell me, who is refinement of whom? Who is refinement whom? So you can easily see that pi 2 is refinement of pi 1. It is refinement. Pi 2 is refined version of pi 1. Yes or no? This pi 2, that is refined version of pi 1. You can easily see, because this is subset of this. This is subset of this. So you can easily see that this pi 2 is refinement of pi 1. Only two partitions are there. Now you can also see that pi 1 is if I define this now on pi, remember on pi, what is pi? Pi is equal to pi 1 comma pi 2. On this, now this is your base set. Please understand, this is your base set. Now this is the base set. Now on pi, I am defining a relation R. I am defining a relation R, and what this relation R is, this is refinement relation. Let me define this relation, refinement relation. And what I am saying that X is related to Y if and only if X is refinement of Y. X is a refinement of Y. Okay, so now you tell me, you can clearly see this relation will have which properties? This relation, you can clearly see this relation R will have which property? It will have reflexive property, because pi 1 is related to pi 1. Similarly, pi 2 is related to pi 2. Every partition is a refinement of itself. Every partition is a refinement of itself. Very simple. This is anti-symmetric also. This is anti-symmetric also. You can easily see that pi 1 is this pi 2 is refinement of pi 1. Pi 2 is refinement of pi 1, but you can notice that pi 1 is not refinement of pi 2. So this is anti-symmetric also. This is transitive also. So finally, this is a partial order. This relation R is a partial order. So if this is a partial order, then what you can create? If something is partial order, then what diagram you can create? You can create a hash diagram, right? Yes or no? So for this partial order, you can create the hash diagram. What that will be? Hash diagram you can create. You can notice that pi2 is refinement of pi1, right? Yes or no? This pi2, this is refinement of pi1. Pi2 is related to pi1, correct? Pi2 is related to pi1. This is your hash diagram because pi2 is related to pi1. Pi2 is refinement of pi1. You can easily see pi2 is related to pi1. So this is the hash diagram. I hope this point is clear. Now let's see the next question. The next question I am asking, now I am giving you this set. Now your set has 3 elements, A, B, C. Now you tell me how many partitions? Pi1, pi2, and so on. Total 5 will be there. Pi1, pi2, pi3, pi4, pi5. There will be total 5. Okay, what are those 5? Let me quickly write them. Pi1 is basically all of them together. Pi2 is basically, it's like something like this. Pi3 is pi3 is something like this. Pi4 is pi4 is something. Pi4 is this ACB, and pi5 is ABC. Again, I am defining the relation. What I am defining on pi relation R. Again, I am defining the relation R. I am saying that X, R, Y, if and only if X is a refinement of Y. X is a refinement of Y. Okay. Again, I am defining this relation. So first of all, you tell me all the properties. Who is refinement of whom? Can I say this is refinement of everyone? Can I say pi5 is refinement of everyone? Yes or no? Pi5 is refinement of everyone. It is a finest partition. Yes or no? This is the finest partition. This is the finite partition. So you can easily see that this pi5, this relates to pi1 also. This pi5 relates to everyone. This relates to pi2 also. This pi5 relates to pi3 also. And this relates to pi4 also. This type of element, what we call it? This type of element, what we call it? This type of element is called list element. Yes or no? Some element which is related to everyone. Some element which is related to everyone. This type of element is called list element. This is automatically minimal also, but this is the definition of list element. So is this clear? This is the list element. So you can see that pi5 is related to everyone. This pi5 is related to everyone. So this pi5 is called what? This is called list element. This type of element is called list, which is related to everyone. Now let's see this. So can you notice everyone is related to pi1? Yes or no? Everyone is refinement of pi1. Yes or no? Everyone, every partition is a refinement of this pi1. This pi1 is the most coarsest partition. So every partition is refinement of this. So everyone is related to pi1. Yes or no? Like this pi4 is related to pi1 because this is refined. This pi4 is refinement of pi1. Clear? So finally, here I can say what more I can say. I can say that look at this. After this, you can say that everyone is related to pi1. Like everyone. For example, pi5 related to pi1. Okay, pi4 related to pi1. Pi3 related to pi1. Pi2 related to pi1 and pi1 related to pi1. This type of element, what we call it? So everyone is related to pi1. Everyone related to pi1. This type of element, what we call it? We call it a greatest element. This is your greatest element. This is the definition of greatest element. Yes or no? Base set cannot be infinite. Yes, it can be infinite, no problem. If you have infinite base set, then number of partition will be infinite. Okay. The properties will not change. Reflexive property, anti-symmetric property, transitive property, they will not change. Partial order you will get. There will be hash diagram. If your base set is infinite, number of partition will be infinite. Okay. So hash diagram will have infinite number of elements. Is this clear? So the properties are not going to change. All these properties, reflexive, symmetric, reflexive, antisymmetric, transitive, these properties are not changing. Are you getting my point? Okay, from the remaining, you tell me. Now forget about pi 1 and pi 5. Forget about these two. In the remaining, who is partition? Who is refinement of whom? The remaining, forget about pi 1, forget about pi 5. The remaining, who is refinement of whom? Who is refinement of whom? Tell me. Who is refinement of whom? Incomparable, very good. None of them is refinement of any of them. So you can easily see that, very easily you can see none of them is refinement of any of them. In the remaining, okay, look at the remaining people. The remaining people, you can easily see these are incomparable. This pi 3, pi 2, pi 4, these are incomparable. Okay, they are not comparable. They are incomparable. They are incomparable. Is this clear? So finally, what hash diagram you will get? Okay, these are incomparable. Incomparable means what? These incomparable. Incomparables, what simply means? Incomparable means, for example, pi 3 is not related to pi 2. Pi 2 is not related to pi 3. Pi 2 is not related to pi 3, and so on. So they are incomparable. Now you tell me what is the final hash diagram. So the hash diagram that you will get, what that will be? The hash diagram will be like this. Yes or no? Like pi 1, everyone is, see, everyone is related to pi 1 because everyone is refinement of pi 1. And this pi 5 is related to everyone. And there is pi 2, there is pi 3, there is pi 4. So you can see this will be your hash diagram. What type of lattice is this? What type of lattice is this? This is your kite lattice. Your famous kite lattice. You can call it K3. Kite lattice K3. Okay. This is your famous. This is not distributive. Yes or no? This is not distributive lattice. This is not distributive. So this is not Boolean algebra. This is bounded, but this is not Boolean algebra. So finally, can you notice that what you are getting that this will be a lattice. I'm telling that you have a set S, then this pi comma refinement. Okay, on set of partitions, this relation, if you notice, this will be a lattice. This will be a lattice. Is this clear? This will be a lattice. All these properties, let's see all the properties of this. So this will be a lattice. This will be a poset. This will be a lattice also. Okay. May not be bounded. May not be Boolean algebra. Yes or no? May not be Boolean algebra. Is this clear? It may not be Boolean algebra. So let's see all the properties of this. All the properties of, so if you have a set S, then for this set S, you have pi comma refinement. Okay, this is your, let's see the properties of this. So what are the properties? Let's one by one. The first property is partial order. Yes or no? The first property is reflexive. The first property is reflexive, antisymmetric, and transitive. This is the first property. The second property is what? This is a lattice. The third property is what? Tell me, this is a bounded lattice. This is a bounded lattice. And who is the least element? Who is the least element? Who is the least element? The least element is your finest partition. Yes or no? Your finest partition is the least element. Okay, your finest partition is the least element. And what is the greatest element? What is the greatest element? This S itself. This S itself. Yes or no? Like this S, this partition which only has one part, this S itself. What other properties you have? What other properties do we have? Need not be Boolean algebra. Yes or no? May not be distributive. Okay, may not be distributive. So this may not be distributive. So I can say may not be Boolean algebra. may not be Boolean algebra. So every property that we have seen, I hope this point is clear. See, this is the partition. Mavit, the partition is this. S is, are you getting my point? Partition is a collection of subsets. Are you getting my point? Mavit, partition is a collection of subsets. Collection of subsets. Is this clear? This is a partition. Okay, but don't worry, like it's not a, for understanding purpose, you can just call it S. For understanding purpose, you can call it S. So these are the properties, all the properties we have seen. I hope you understood this chapter. Now let's see this question. A beautiful question on this topic. Let's see this one. What about this one? Let's see this question. Consider the set. A set is given to you A, B, C, D. For this set, did he give us all the partitions? Tell me, did he give us all the partitions? Remember all the properties I told you, these are for all the partitions or for some of the partitions? The properties that we have seen, here this pi is a set of all partitions. Yes or no? Set of all partitions. So please understand, this was set of all partitions. This pi was set of all partitions. So for all the partitions, we had these properties. But now the question is saying that only 4 partitions are given to you. This is a GATE 2007 question. A set is given to you A, B, C, D. 4 partitions are given to you, pi 1, pi 2, pi 4, and so on. Now, these partitions are given to you. Like here you have only one part A, B, C, D. Here you have 2 part A, B, C, D. Here you have 2 part A, B, C, D. And here you have, this is the finest partition. Yes or no? This is your finest partition. Now let's move on. Now let's see this. So the question is saying that you have a partial order on this set of partitions. There is a partial order you are defining, and you are saying that this is related to this if and only if pi I refines pi j. Okay, means this pi I refines pi j. Then what is the hash diagram for this? So this is very easy. You can easily see. You don't need the remaining options. You just create it. You just solve this question. Forget about options. You just solve the question. So you can see that there are 4 partitions. Okay, we have total 4 partitions. There is pi 1 in which you have A, B, C, D separate. In the pi 1 you have all of them together. In the pi 1 you have all of them together. In pi 2 you have A, B, C, D. In pi 3 you have A, B, C, D. And in pi 4 you have what? In this you have A separate, B separate, C separate, D separate. Simple question I am asking. Can I say pi 4 is related to everyone? Pi 4 refines everyone, yes or no? Simple question. Can you see pi 4 refines everyone? Pi 4 refines every partition, every pi I, every partition, yes or no? So this every partition. So this is actually the finest partition. This is called finest partition. So this is basically the finest partition. So this will be on the bottom. Agree or not? Definitely this pi 4 will be on the bottom. This pi 4 will be the least element because this will be related to everyone. Okay, this is going to be related to everyone. So this definitely will be at the bottom. What about this pi 1? What about this pi 1? This is the, I can say, this is the coerced partition. This is the coerced partition. You can notice that everyone will refine it. Yes or no? Everyone refines it. Every pi I refines pi 1. Okay, so I can say that this pi 1, basically this is your greatest element. This will be your greatest element. It will be greatest, like, because everyone will refine it. Okay, everyone is going to refine it. What about pi 2, pi 3? What about these two? Pi 2, pi 3. What about these two? What about these two? These two. They are incomparable, right? Yes or no? They very good. They are incomparable. They are incomparable because you can notice this pi 2 is not refinement of pi 3 and pi 3 is not refinement of pi 2. Yes or no? You can clearly see pi2 does not refine pi2 does not refine pi1. Why? Just apply the definition. Arey, why? Tell me why. Just apply the definition. Pi2 does not refine pi1. Why? Because you can clearly see this is not subset of anyone. This CD is not subset of anyone. This CD, it is not subset of any part. This part, look at this part is not subset of any part. Similarly, pi1 does not refine, sorry, what I'm saying, pi2 does not refine pi3. Similarly, pi3 does not refine pi2. Okay, you can see that. Very simple. Pi2 does not refine pi3. This pi2 does not refine pi3 because this is not subset of any part. Similarly, pi3 does not refine pi2 because this is not subset of any part. So finally, these are incomparable. Your final diagram will be what? Your final diagram will be pi4 in the bottom, then pi2, pi3 here, and then pi1 here. Okay. So this will be your final diagram, and the answer that you will get, you can check the options are these. So there is one option here. Okay, this option will be the answer. The answer will be option C. I hope this point is clear. Tell me, is this crystal clear to everyone? But okay, tell me, if I consider all the partition, how many elements will be there? See, this set is given to you. This set S is given to you. There are A, B, C, D, 4 elements are there. If I consider all the partition, if I consider this pi, let this pi be set of all partitions. Okay, then this pi will have total how many? Total 15 elements with this pi will have, correct? Because there are 15 partitions. Because there are 15 partitions of S. This S has total 15 partitions, so there will be 15 elements. Okay, and for this pi, if you do this, now remember for this pi, if you have this relation, refine relation, this refine relation that you have with pi, now what are the properties? Tell me. Now what will be the least element? The least element again will be so this will be a poset. Again, this will be a poset. This also will be a lattice. This will be a poset. This will be lattice. The least element will be the finest partition. The least element will be like this: A, B, C, D. This will be the least element. The greatest element will be all of them together, and so on. So ultimately, it will be a poset. It will be a lattice. So that's it. I hope you got it. Now let's see this question. Can you solve it? Question number 11 in GATE Computer Science 1998. This set is given to you, and pi1 is this partition ABC, D. Now the question is saying that the partition is given to you. Now list the ordered pairs in the equivalence relation induced by this partition. Yes or no? This is see. Partition will give you equivalence relation, and equivalence relation will give you partition. Yes or no? Okay, we already know that if you have a set, let's assume you have a base set. This we already know that you have a base set S. Then for this base set S, if you take any partition of S, okay, that will give you equivalence relation. Okay, from that you can create a equivalence relation on S. From that you can do this, and from this equivalence relation you can get partition. Okay, very simple. Now you tell me here in this one, what will be the cardinality? Like basically this partition will work as the equivalence class. Yes or no? Correct. So this part A, let's solve this part A. Let me solve this. So the set that is given to you, this is the base set in which you have 4 elements A, B, C, D. Okay, so this is the base set, and in this base set you have total 4 elements. This is the set. Now the question is saying that consider this partition. A partition is given to you. In the partition, he is saying that basically ABC together, D separate. ABC is together and D is separate. So if you want to find the corresponding equivalence relation, then how? Okay, then for that, what will be the equivalence classes? If you want to find the corresponding equivalence relation, then these will work as the equivalence classes, correct? Yes or no? These are the equivalence classes, these two. So very easily. So these are the equivalence classes. Like this is your set A. For this set A, you can see that these are the equivalence classes. Here you have 3 elements A, B, C. Here you have 1 element D. So what will be the relation R? In the relation R, what will be the cardinality? The relation R, you can see, let me call this A1, let me call this A2. Now you tell me what relation R will be. R will be A1 cross A1. Yes or no? A1 cross A1 union A2 cross A2. Because every element here will be related to every element here. Every element will be related to every element. Every element will be related to every element. So it will be like, okay, A1 cross A1 union A2 cross A2. What will be cardinality of R? Now you tell me about the cardinality of R. That will be 3 into 3 plus 1 into 1. Okay, the answer will be 10. The cardinality of R will be 10. Is this clear? From here you will get 9 pairs because every element will be related to every element, and from here you will get 1 pair. So this is the R, and the cardinality of R will be 10. And you can also write the R like this. So basically A will be related to A will be related to B, A will be related to C. Okay, and so on. B will be related to A, B will be related to B, B will be related to C, C will be related to A, C related to B, C related to C, and finally D related to D. This is your cardinality 10. Cardinality of R is 10. This is your question number 1. So question number 1 we have done. Equivalence relation he was asking, we have done it. Now the second question, draw the graph of that equivalence relation. Draw the graph. Can you draw the graph of that equivalence relation? Very simple, because it's like A, B, C, and there is D. So these are related to each other. Okay, and there is reflexive pair. So this is the graph. Very simple. This will be the graph. Okay, this is your part B. Now let's see, the part B is also done. What about part C? So pi 2 is given to you, pi 3 given, pi 4 is given. Posset diagram you have to create. Posset diagram, these and refines. So what your answer will be here in this one? You can easily see pi 2 will refine everyone. Yes or no? Correct. Pi 2 will refine everyone. And pi 3 is the, everyone will refine pi 3. See, pi 2 will refine everyone. And everyone will refine pi 3. Everyone is going to refine pi 3. And these are not comparable. Pi 1, pi 4. Pi 1, pi 4, these are not comparable. So the answer will be this. Okay. So this is the answer. Very simple. I hope this is, I hope you understood this. Very simple. Okay. This is not the diamond lattice. Akash, this is not diamond. Is this clear? Akash, diamond is this. This kite lattice is also called diamond. This is not diamond. Kite lattice is also called diamond. The another name of kite lattice is diamond. So this is your chapter. This is the chapter of refinement. I hope you understood. One very interesting application I want to give you. This is the last thing. Very interesting application I just want to give you. This refinement. Have you seen this refinement in theory of computation? In the theory of computation subject, have you seen this refinement? In the theory of computation subject. Very interesting thing I want to give you. Let me tell you. Okay. See, DFA, NFA. Let's come to DFA. Whenever you have some language, consider this language L. I am giving you. This language L is, let's assume, sigma star. I am giving you a DFA for this language. Consider this DFA. Consider this DFA Q0. Okay, or maybe I can say P0. Consider this DFA for sigma star. On A, you go here. Okay. On B, you stay here. On A, you go here. On A, you go here. On B, you stay here. Is this correct DFA for this language? Is this correct DFA for this language? For this language, is this correct DFA? Yes, this is your D1 DFA. Can you merge these two states? Can you merge these two states? Yes, these are equivalent, right? These two states are equivalent. Okay. So yes, you can merge them. So you can basically, you can get a new DFA you can get. Okay, let's call it D2. Can I say, okay, if you are merging, you are getting here. Can I say if you split, you are getting here? So what I want to tell you, who is refinement of whom? So you can notice D1 is refined version of D2. Yes or no? You can notice D1 is refined version of D2. So something that interesting, that is very interesting. This is what I want to tell you. And I hope this question comes in the GATE exam. I really, really hope, because this is something that only Go classes students will be able to answer. This is something, another interesting thing I want to tell you. And this is that, see, basically this D1, can you notice this D1? Look at this DF at D1. Can I say this is a split? This is a split version of D2. Can I say? Yes or no? So you can easily see that this D1 is refined version of D2. So what statement can I give? Okay, let me give more. Let me give you more examples. Consider this example. See, consider this example. This is from IISc. Let me tell you, the source is IISc. Okay, now let's see. So tell me, look at this one. Look at this DFA. This is minimal DFA, right? Yes or no? This is the minimal DFA. Now. When you create minimal DFA, you go from this direction to this direction. Do you agree? Do you agree that when you create minimal DFA, then you go from this direction to this direction? What you will do? You will merge equivalent states. Okay, this is what you will do. You will merge equivalent states. You will merge, for example, these will be equivalent states. This you can check it out. This P comma T, these are the equivalent states. Q comma S, these are equivalent states. You will merge them. You will merge equivalent states, and what you will get? You will get minimal DFA. So in the reverse direction, can I say this is, you are basically splitting? Yes or no? Like in this direction, from this direction you can go to this direction. Then what you will do? These you will merge into one state, and these you will merge into this state. So you will merge the equivalent states. Okay, so basically here you are doing the merge equivalent states. Now in the other direction, what will happen? In the other direction, what will happen? In the other direction, what will happen? Basically you are refining. Yes or no? You are splitting a state into equivalent states. Isn't it? Tell me, isn't it? Like this state you are splitting into equivalent states. Look at this state. Look at this state. Please see this. This state you are splitting into two states. What you are doing? Basically, on A you go here, on B you go here. See, on A comma B you are going here, on A comma B. Now what you can do? You can split this state into two states such that on A you go here, on B you go here. Similarly, on A comma B you go to this state. What you can do? You can split. On A you go here, on B, something like this. So you can just check it out that you are splitting any state. You are splitting state. You are splitting. Okay, you are splitting a state into equivalent states. So can I say who is refined? Who is refined? This is refined. Yes or no? So I can say this is more refined. So you can easily see that. You can easily see. Let's call it D2. Let's call it D1. Now you can easily see that D2 is refined. D2 is refinement of D1. Okay. So finally, the answer will be what? This is the statement that I want to tell you, that you can see that for any regular language, this will happen. See, for any regular language, every DFA, for any regular language, every DFA is a refinement of minimal DFA. Is this understood? This is only for DFAs, remember. This is only applicable for DFAs, and we are saying that every DFA is a refinement of minimal DFA. Yes, yes, Mavit, very good. Minimal DFA is the coarsest version. I know this is not it sounds very odd, right? Yes or no? That minimal DFA is basically the coarest version. The coarest version, the coarest DFA. Okay, so it sounds very odd, but that's you understood, right? You understood the definition. See, tell me, you understood this, correct? Because you are splitting is you're splitting any state into equivalent states. So for example, this state you split into two states. So can you see this is your refinement? Akash, Mavit, tell me. This is refinement. This is called refinement. This is called refinement. This is called refinement. That's it. Okay. Refinement is this, that you are splitting this into two, further split. So very simple. This is the node. And I hope that this comes in the GATE exam. This is my sincere hope that this should come in the GATE exam. Okay, they must ask this in the GATE exam. They should define it. Let me tell you what they should do. See, they should give the complete definition. A paragraph they should give. Okay. Some paragraph they should give, everything should be defined. So that question is very nice. Okay. The paragraph is given and then finally they ask you this. Some true false question, some MSQ question, they ask you this. So I hope this comes in the GATE exam so that goclasses students will get some, I can say, some advantage. So anyway, this is the final point. This is the application. Is this clear to everyone? The application of refinement in TOC, in theory of computation. So every regular language, for every regular language, every DFA, remember every DFA is refinement of minimal DFA. Okay. So thanks. This is complete. This is the final. Similarly, here also you can see that one state you are dividing into two states. Okay, one state you are dividing into two states. So similarly, here also you can check it out. Okay, that's it. So okay. Anything else? Yeah, this is the complete summary. And finally, one more thing I want to tell you. In the equivalence relation, when can you say one equivalence relation is a refinement of another equivalence relation? So if you have, let's assume there is a set A. And on this set A, let's assume you have two equivalence relations. This we have already seen. Equivalence relation. Let's assume you have two equivalence relation R1, R2. Okay, there is equivalence relation this. So when can I say R1 refines R2? When can I say R1 refines R2? When can I say that? R1 refines R2. When the equivalence classes, basically the set of equivalence classes of this, or I can say that should be refinement of this. So I can say that R1 refines R2. When it will happen, tell me. When it will happen that R1 refines R2. It will happen when R1 is subset of R2. Yes or no? Why? What is the reason? See, R1 refines R2. Yes or no? It means that some refinement will happen. Some refinement will happen. So if some refinement will happen, then what will happen? Some refinement will happen, then what will happen? Then the cardinality will reduce. This R1, can you notice this? Here, everyone here is related to everyone here. And here what will happen? Only these are related to themselves. These are related to themselves. So tell me who is subset of whom? Tell me who is subset of whom? Please see this. R1 refines R2. This R1 is refining R2 means, so who is subset of whom? So you can easily see that R2 is superset, R1 is subset, right? Yes or no? Array, look at this. Here everyone will be related to itself. Like, let me give you example. If you are confused, let me give you this example. See, consider this example, like consider this relation set. I am giving you a set S in which you have four elements A, B, C, D. Now you have two equivalence relations. There is R1, there is R2. There is equivalence relation R2. Okay. Now assume that in this R1, let's assume this is the partition happens. That AB here, CD here. And this R2, what happens? This partition happens. This A here, B here, CD here. Now you tell me. Now you tell me. Now you tell me who is a refinement of whom? Who is a refinement of whom? Simple question. Very simple question. Who is refinement of whom? Can you see that this R2 is refinement of R1? Yes or no? Can you see this R2 refines R1? And you can also see that this R2 refines R1 and you can see this is subset of R1. This R2 will be subset of R1 because here they are related to each other. Here they are separate. So you can notice R2 refines R1 means R2 is subset of R1. I hope this point is clear. Now, similarly, you can see if I give you this, is this refinement? Who is refining whom? Like AC, BD. Who refines whom? Who refines whom? This does not refine this. See, this does not, this you can easily see this does not refine this, and similarly this does not refine this. They do not refine each other because you can see they are not subset of each other. Okay, they do not refine. So this is the final point, that you have two equivalence relation. When can you say R1 refines R2? If and only if R1 is subset of R2. Okay, is this clear? R1 refines R2 if and only if R1 is subset of R2. If and only if. Okay, that's it. So everything we have seen. So can I say that a simple thing, this is just a simple thing. Can I say this? Look at this last one. Can I say every equivalence relation is subset of A cross A? Yes or no? Every equivalence relation, look at this. Two equivalence relation, R1 refines R2 means R1 is subset of R2. So can I say every equivalence relation is refinement of A cross A? That's it. Okay. Because every relation is subset of A cross A. So every equivalence relation is refinement of this. Can I say identity relation? Can I say identity relation is the refinement of every equivalence relation? Identity relation is the refinement of every equivalence relation. This identity relation, this will be refinement of every equivalence relation. So that's it. This is your chapter. So we are done with this. We know that. So all these things. Okay. So this is your chapter. Please tell me if anyone has any doubt. This is your complete chapter, complete analysis. I can tell you, I can guarantee that no other question can be created. We have seen the definition. See, what was the sequence? We started with what is partition? What is partition of a set? That concept we have seen. Partition of a set. Okay. We have seen the partition of set. Then we have seen analogy of refinement. Those two analogy, do you remember? Those two analogy. One is India, Pakistan, Bangladesh analogy. Another is Apple analogy. You know, mother partition, girl partition, boys partition. So Apple analogy. These two analogy. Now, after that, we have seen the definition of refinement. One partition refines another partition. The definition we have seen. Then we have seen some questions, some nice questions. How many refinements are possible? Who is refinement of whom? Okay. So this type of questions we have done. After that, we have seen the properties of refinement. Okay. Like you can see what is the finest refinement, what is the maximum refinement you can do, what is the minimum refinement, what is the finest refinement. Like every element is one part is one element, that is finest refinement. And what is the, I can say, worst refinement, what is the coarest refinement, that is your basically the entire set. Okay, basically you have only one part. Okay, so that we have seen. Then we have seen some properties, that if you have set of all partitions, okay, if you have set of all partitions, then what are the properties? Refinement relation is reflexive, transitive, antisymmetric. Okay, so these three properties, it simply means that refinement relation is partial order. Okay, if it is partial order, you can create hash diagram. Also, refinement relation on the set of all partitions. This is very important. See, in the two gate exam questions, did you notice they did not give you all the partitions? There are two gate exam questions. They did not give you all partitions. They gave you only 3-4 partitions. 4 partitions they give you. They did not give you all partitions. But if you have all the partitions, okay, set of all the partitions, if you have, then if you use this refinement relation, then you will get a partial order, reflexive, antisymmetric, transitive property. You will get a lattice. The least element will be the finest refinement, because that will refine everyone, and the greatest element will be the worst refinement, because everyone will refine it. Okay, and then we have seen that it will be a lattice, but it may not be a Boolean lattice. Okay, it may not be a Boolean algebra. It will be a lattice. It may not be a Boolean algebra. Okay, so these things we have seen. After that, we have seen applications of this two gate questions we have done. Okay, all the complete analysis of those two gate questions we have done. After that, what we have done? Applications. Okay, application in the theory of computation. That is very interesting application, that every DFA is basically refinement of minimal DFA. That is something odd. Okay, that is something I can say not intuitive, that every DFA is basically refined version of minimal DFA. Okay. Yeah, like every DFA is finer than minimal DFA. Okay. Yes or no? Every DFA is finer than minimal DFA. So that is something which is not intuitive, but it happens. Okay. It is what it is. Now, the next is application in equivalence relation. So we can say one equivalence relation will refine another equivalence relation, like R1, this is an equivalence relation, R2, this is an equivalence relation. R1 refines R2 if and only if R1 is subset of R2. Okay. And then you can notice that every equivalence relation is a refinement of A cross A. Yes or no? Every equivalence relation, whatever equivalence relation you take, that is refinement of A cross A, because every equivalence relation is subset of A cross A. Also, identity relation, that is refinement of every equivalence relation. This is your complete summary, complete chapter. Let me tell you, in the entire internet, you will not find extra details. These are all the details that are possible. These are all the details that are available in the entire internet. Okay, so this chapter I just wanted to this is not much important from the gate exam point of view. Okay, this refinement, there are two gate questions. If you just forget about these two gate questions, then this chapter is not much important. But we have seen the complete analysis. I hope you understood, and I hope you will never forget. That is important. See, you understand it right now and you forget in the gate exam. That is not good. That is the reason I have given you the analogy, so that you can remember the definition. And once you remember the definition, we have proven everything. Okay, analogy I have given so that you can remember the definition. Once you know the definition, then complete analysis we have done with proof. I have given you the proof. Okay, so once you have the definition, you can do entire analysis, the complete analysis you can do. Okay, so thank you everyone.